Okay, after that long slog of a theorem, we now can reap all the rewards. So suppose we have a finite normal extension inside C. So L is finite, L over K is finite, but L is also equal to its normal closure because it's already normal. Okay? Then there are precisely L over K distinct K automorphisms of L. Proof. Or I guess, sorry, there's one more bit here. That is, the order of the Galois group is the degree. What a wonderful equation. Wonderful. This is wonderful. Wow. Proof. By the theorem, there exists precisely the degree of L over K, K monomorphisms from L to the normal closure, but L over K is normal, so it's from L to L, and any K monomorphism from L to L is an automorphism because L over K is finite. So we get exactly L, the degree of L over K, no more. And the number of distinct K automorphisms from L to L, that's just the number of elements of the Galois group. Okay, so that's it. Wow, wonderful. Theorem. Let L over K be a finite extension. Color it in. With Galois group G. If L over K is normal, then the fixed field is K. Is the fixed field of the Galois action. This is simple. Let's prove it. Proof. Well, if L over K is normal, we know it's finite, then the order of the Galois group is the degree of L over K. But we also know that whenever you have a finite group of automorphisms of an extension, the number of automorphisms is the degree of L over the fixed field. And that was something we proved in the last chapter on counting principles. So we have a tower. We have a tower K is contained in the fixed field, because certainly everything in G fixes K, so it's contained in the fixed field. It's contained in L. And we know that in this tower, the big extension and this intermediate extension, these both have degree the order of G. Well, what must be true then? Well, if they both have the degree the order of the G, then the first guy, this first guy here, must have degree 1. So the fixed field is exactly K. Wow, wonderful, wonderful theorem. Let's do another theorem. These are going fast because we spent all that time on the proof of the last theorem. So suppose K is contained in L is contained in M, and M over K is finite. Then the number of distinct monomorphisms K monomorphisms L to M is at most the degree of L over K. Proof. Let N be the normal closure of M over K. Then the collection the set of all k monomorphisms, L to M, is if you have a k monomorphism from L to M, we can then further map it to N. So this is contained in the collection of all k monomorphisms from L to N. You just further include M into N to see that containment. Okay, so not all of the monomorphisms will be monomorphisms to M. Some of them might leave M because M is not given to be normal. So not all of them will be, but some of them might be. Okay, so let's continue. Thus, the number of such monomorphisms from L into M is less than or equal to the number of monomorphisms from L into N. And we just saw in the previous theorem that's at most the degree of, well, that's equal to the degree of L over K, but we could have less, so less. All right. The last theorem in the chapter, might as well just bang it out here. I did skip one of the theorems in this chapter because it was unnecessary. But nevertheless, last theorem of the chapter is if L is any field, G any finite group of automorphisms of L. Wait, I'm not going to say K automorphisms because we don't have a K, we just have a field. And we let K be the fixed field. Okay, so now they're K automorphisms because G fixes them. Then what? Well, L over K is finite and normal. With G being the Galois group of L over K. So it's saying any finite group of automorphisms is the Galois group of some extension, and it's this particular extension where you take the fixed field as the thing you're extending. Okay, proof. Last proof of the chapter. So we know that the degree of L over K is the order of the group because K is the fixed field. And let's say that that's it. And what? And I'm looking over the notes for this, and I think I'm going to omit the proof. I'm sorry, because it relies on the theorem that I did not prove. But maybe I'll do an addendum video next week when I have a little more time. So I'm gonna go ahead and omit the proof of this theorem, but I might come back to it. So sorry about that. Just a little pressed for time this week. Okay, so let me just say one more time here what we've seen. When you have a finite normal extension, the degree of the extension is precisely the number of elements in the Galois group. Okay, if you take away anything from this chapter, please take away that. And that's it. So that's the end of chapter 11.